All right, welcome everyone. I hope everyone's doing well. Monday morning. I'm going to start talking about a new topic today, food additives. So lots of different types of things here. So I'm going to spend just a few slides talking about various things that are added to food. So first of all, we have a couple definitions. We have something that we put directly into the food, so a direct additive or just an additive, something that would be on the ingredient statement. We then have an incidental additive, which is something that is incorporated into the food during processing, typically. Lubricating grease from machinery can sometimes get into the food. Gases, sulfur dioxide or chlorine that we might use to bleach flour would create some, unintended compounds in the food. And then preservative is just something that extends the shelf life. And it could be microbial growth inhibiting or chemical reaction inhibiting. So first of all, we'll just talk about some acids. Acids are very common food additives. And so we have several of them that we are going to put into foods. So we'll just go through them. I have them listed by how many carbons they have for the organic acids. And then at the bottom, we have the inorganic acids, the mineral acids. So we'll just go through these names here. The 1-carbon formic acid is actually not added to food, but it's very common in animal feed. We'll talk about that in a second. C2 acid, what's this one? Everyone should know that one, yeah. Okay, good. Now we get to the 3-carbon acids. Anyone know what either one of those two are? By the way, anyone listening online, I do have the chat open if you want to answer some of these questions. Both of these, well, at least one of them is really common. You would have heard it before, for sure. Dairy products, fermented dairy products. Lactic acid. Lactic acid is the one on the left. And then the one on the right would be just this aliphatic acid, propionic acid. I should put the acid form. C4, these are maybe ones that you may not know already. The one that has the 2 hydroxyl groups, so we'll go from left to right again. That one is tartaric acid. So tartaric acid is a common acid in fruits, and it's the predominant acid in grapes. Next, we have malic acid. Malic acid is common acid in fruits as well, very predominant in apples and also peaches. And then the last one there is fumaric acid. Okay, 6-carbon acids. So that the one on the left there should be immediately recognizable. So 6-carbon acid with 3 carboxylic acid groups on it. You know what this one is, right? The most common acid in fruits. Citric. This one here in the middle is sorbic acid. And then adipic acid. And then this acid with 7 carbons here has that benzene ring, so it's benzoic acid. So these would be, really common acids, with the exception of formic, that we would add to foods. And then we have hydrochloric, phosphoric, and sulfuric. So all of these acids have their place in food processing. With the exception of phosphoric acid, these mineral acids are typically not added directly to foods. So, but they are very common in food processing. So if we look at a couple of acids that I have there in boxes, I boxed those because they have unique functionality. So most of these acids would be added to foods for their acidic nature. Because they're acid, you want to lower the pH, you want to impart some sourness, something like that. But the ones that are here in boxes would not be typically added because of their acidic character. So formic acid is in a kind of a brown box there, a little bit different. Like I said, that one's not used so much in human food, but extremely common in animal feed. A lot of times it is sprayed over animal feed just as a preservative, prevent microbial growth in that animal feed. But the ones in the red boxes, those are the preservatives in human food. So they're not added because they lower the pH so much as they have certain antimicrobial properties that are important, and we'll talk about them. So the propionic acid, C3, sorbic acid, the C6 one, and then benzoic acid. All of these are added to foods for their preservation qualities and their antimicrobial properties, not typically for acidifying foods. So I thought we'd just have some foods up here and talk about the acids in them. So oranges, of course, we would think immediately of citric acid. That's where citric acid gets its name, is from citrus fruits. So we have lots of citric acid in those citrus fruits, as well as basically every fruit is going to have lots of citric acid. Maybe not the predominant acid, but it's going to be present in some concentration or another. Next, we have some tortillas, a non-acidic food. And so we actually have some of those acids that are added for different functions. So one of the acids in tortillas would be fumaric acid. So one of those C4 acids. And fumaric acid has a unique functional property when added to wheat flour-containing foods. So what it does is it relaxes the gluten. So, gluten's very elastic, right? So makes it hard to roll out a tortilla because it just wants to shrink back into a ball. And fumaric acid will make it easier for that to be rolled out. Also, you do have propionic acid and sorbic acid in flour tortillas, only there for their antimicrobial properties, mold inhibition and yeast inhibition. So again, non-acidic food, but we've got 3 acids in there that are added. Relish, of course, that's going to be acetic acid. So these pickled type products are going to have lots of acetic acid in them, and that's, very familiar flavor. On the bottom row, we have Coke or any kind of cola beverage. So this is the unique type of product where we add a mineral acid directly to that. So phosphoric acid is an actual ingredient in these cola products. And added there mostly for preservation, trying to get the pH low, but we don't want a sour taste to this because this is not a fruit kind of flavor. So we would have, we can have phosphoric acid, which is not sour, but can lower the pH. And then also, you know, it can be a chelator, so it can help with some preservation of flavor quality. I mentioned already in the apple, what's the predominant acid there? Malic acid, yeah. And then I have some cranberries there. Cranberries are, you know, principally the acid in cranberries would be citric, just like the oranges. But I put the picture up there because cranberries are uniquely high in benzoic acid naturally. So benzoic acid, like I mentioned, is an acid that typically is added just because it can control microbial growth, but it is present in foods naturally, and cranberries, it's quite high. So acids, in addition to just lowering the pH, can be buffer systems, and those can be very important for controlling the acidity and also keeping the pH, you know, what it needs to be. So this is just an example of a titration of citric acid. So you've got citric acid with 3 carboxylic acid groups on it. And so at very low pH, you're going to have all the acidic protons are going to be there. So it's going to be fully protonated. As we raise the pH up to the pKa, so at pKa 1, which was pH 3.1, what does that mean? What does pKa mean? That's exactly right. So at pH 3.1, you're going to have 50% of this and 50% of this. And so a acid is going to be a good buffer at that pH, right? Because you're going to have these two species that can, if you add a bunch of protons, it can suck them up. Or if you add a bunch of, you know, alkali, it can suck that up. So it can keep the pH, you know, constant. So, and then typically we think of these acids as being good buffers, you know, plus and minus 1 pH unit from the pKa. So at 3.1, we could, this, you know, this proton here that's coming off first, you know, it can buffer between 2.1 and 4.1. Because we have 3 acidic protons, we can raise the pH up a little bit more, and the second proton starts coming off. The other one on the end, you know, this is, we can flip this. So both of these protons are the same, but one of them will come off and then the other one starts coming off. So at pH 4.7, we would have 50% of this and 50% of this. And then finally, this last one will come off at a near neutral pH. So citric acid's pretty unique because of its 3 carboxylic acid groups. It can basically buffer at any pH, you know, below 7 or below 7.5. So that's pretty unique. So this is just some pKa's of some different acids that we've talked about. And then, you know, what pH range they're good buffers. So you'll see, you know, it's just plus and minus 1 from the pKa. So this phosphoric acid, the first acidic proton, you know, can buffer between 1.1 and 3.1. So here's some more foods. We have several that are containing buffering systems. So Doritos, these are Cool Ranch Doritos. So I'm talking about the flavoring on the outside of the Dorito. The actual chip isn't going to have buffer systems, but the flavoring on there's got a lot of buffers in it. Some lactic buffers, mostly lactate buffers are going to be there on the outside of those chips. And some acetate buffer as well for the flavor. For bologna, there's lots of different buffers that are there for keeping the pH stable during processing. So we have in bologna, we have sodium diacetate, so the salt of acetic acid, where we have 2 acetic acid groups and a sodium ion in the middle of them. And we also have sodium lactate and potassium lactate. So these are going to be chelating agents. These are going to keep the pH stable and control the flavor and all that kind of stuff. Sunny Delight, this is a orange flavored beverage that would be much less biting or much less of a strong sour flavor than orange juice would have. So in Sunny D, instead of just citric acid, we've got citric acid and sodium citrate to create a buffer a little bit higher so the sourness isn't as strong. So yeah, we see here it's smooth and sweet. Jell-O has a lot of buffers in it, but the main buffering system would be adipic acid, and then either some kind of phosphate, or it could be another kind of organic acid like sodium citrate. And it's really important to have these buffers in here because it's really common for people to put other fruits in these. So instead of just making strawberry banana Jell-O, you might put in some strawberries, or you might put in some other kind of fruit, and that fruit's going to have some acid to it. And if you lower the pH of that, then the gelatin takes longer to set. And so then the box instructions would be wrong, because it would take more than 4 hours to set, or more than 1 hour if you're doing the quick set. So those buffers are there to keep that pH high so that it will set faster, and so that the box directions will be correct. Somebody's lunch party won't be ruined. Next would be Sprite. This is a citrus flavored beverage, so it's going to have citric acid and sodium citrate in it. So as opposed to the cola beverages that you don't want that sour flavor, here you do. So you're going to have a combination of citric acid and sodium citrate. All right, so moving on to a new topic here, chemical leavening. So we're going to talk about a base that's added to food now. So first of all, baking soda, that's just sodium bicarbonate. So all it is this chemical sodium bicarbonate, which has this formula here. And in the presence of heat, so if we heat up sodium bicarbonate to above 80 degrees Celsius, it will spontaneously decompose to sodium carbonate, without that extra H there. So sodium carbonate, water, and carbon dioxide. So if we take a product that contains sodium bicarbonate and heat it up, we can leaven that product because it's going to let off carbon dioxide. But in this process, it's also going to make sodium carbonate, which is alkaline. So the pH of that product is going to go slightly alkaline, maybe pH 8, pH 8.5. So that's what will happen if we add this sodium bicarbonate to something without any other acid present. So it can spontaneously decompose above 80 degrees and leaven the product by itself. More commonly, though, we will put an acid, mix an acid there with the sodium bicarbonate. So this equation down here is showing what happens when we have an acid present. We have sodium bicarbonate and any acid. I just have this X for this acid. And this will react at room temperature, any temperature, and produce carbonic acid, this carbonic acid right here, and the sodium salt of the acid that you added. And carbonic acid is a strong acid, decomposes spontaneously to water and carbon dioxide. So we have leavened the product this time at any temperature by adding an acid. So let me mention one other thing here. Sodium bicarbonate is basically what we add to all chemically leavened baked products as the leavening base. There are some rare exceptions, like if you're concerned about sodium in foods, you want to make a low sodium food, you might use potassium bicarbonate. The only reason to use potassium bicarbonate would be because you're concerned about the sodium in sodium bicarbonate. Because potassium bicarbonate is more expensive, you have to use more of it because the potassium ion is heavier, so you get less bicarbonate for every weight of stuff that you add. So you have to use more of it. More expensive. And also, one really important thing with potassium bicarbonate is that it breaks down at a higher temperature. This one, 80 degrees. Potassium bicarbonate breaks down at 100 degrees Celsius. How long do baked goods, breads, muffins, cookies, cakes, how long do those products maintain a temperature above 100 degrees when they're baking? They don't. Never. So that potassium bicarbonate is never going to break down. You know, you're in an oven that's, much higher than 100°C, but in that product, the water there, the water present, is going to keep it at or below boiling water temperature. So maybe on the very surface you would get some breakdown, but within that product, by the time it's done, you're taking it out, it's still not going to be 100 degrees Celsius in the center of that product. So, so you must, if you're using potassium bicarbonate, you must use an acid to break it down. It will not break down spontaneously under normal baking conditions. And then another kind of niche market would be ammonium, either ammonium carbonate or ammonium bicarbonate. And each of these could be leavening bases. Ammonium carbonate and bicarbonate break down at very low temperatures, about 60 degrees Celsius. So you would not need an acid to mix with these. Typically, you would not add an acid. So they're really common in very dry foods. So you could think about pretzels or ginger snaps. They're really common. So has to be in something very dry, because once it comes out of the oven, if you've got any moisture there, the ammonia from the breakdown of the ammonium bicarbonate or carbonate will dissolve in that water, and the product will taste like ammonia, which is terrible. So you can only use it in products that are going to be exceedingly dry when they come out of the oven, like the things I mentioned: pretzels, ginger snaps, some kinds of crackers. Yeah, but the nice thing is that it breaks down by itself and there's no byproducts, because the ammonia comes off and the water comes off. Okay, so but the interesting part about chemical leavening then is not so much the base, but the acid that you use. So lots of different choices for acids that you would mix with sodium bicarbonate to leaven a baked good. So this is a graph showing a couple of different options. So very common just to put some abbreviations for these. And they're commonly just called their abbreviations. But I have the names written out down here. But what you see is that over time, the carbon dioxide is released from the mixture of that acid and the sodium bicarbonate at different rates. So monocalcium phosphate, this one releases acid very fast, right? So as soon as you mix those two ingredients together, lots of carbon dioxide is going to be released. And in contrast, if you use anhydrous monocalcium phosphate, that would have some kind of coating. A lot of times it would be like an alumina coating or something to sort of slow down the reaction. Then the release of that carbon dioxide is much slower. So we would call this one here, anhydrous monocalcium phosphate, a slow-acting acid. And this monocalcium phosphate here would be a fast-acting acid. We have here SALP, sodium aluminum phosphate, also a slow acid. You see it releasing that carbon dioxide very slowly. And actually, much less too, right? Much less here, because it doesn't really react at 27 degrees. This is at 27 degrees. So if we heated that up more, then we would get more CO2 from that sodium aluminum phosphate. So these two would be slow-acting acids. This one would be a fast-acting acid. So that's where we get that term double-acting when we look at baking powder. So both of these here, if you look on the side here, it says double-acting. Here's double-acting baking powder. So double-acting means it's going to have both a fast-acting acid and a slow-acting acid together with sodium bicarbonate. So I have the ingredients here. Cornstarch is just a filler. That's going to keep the product free-flowing and also keep the particles of acid separated from the particles of base. We have sodium bicarbonate. That's the base. It's always going to be that. Typically, these baking powders will have about 30% sodium bicarbonate. And then we have sodium aluminum sulfate, which would be similar to the sodium aluminum phosphate that we saw in the previous slide. So that would be a slow acid. And then we have monocalcium phosphate, which we saw in the previous slide was a fast-acting acid. So we have here double-acting because we have a slow acid and a fast acid mixed together with that sodium bicarbonate. In this one, this is aluminum free, so we aren't going to have the aluminum salts. This one only has 3 ingredients: cornstarch, sodium bicarbonate, and monocalcium phosphate. So it looks maybe like it's not double acting. What these have typically, they have monocalcium, they have anhydrous monocalcium phosphate and the monohydrate monocalcium phosphate. So they have both of these too. But on the label, it just says monocalcium phosphate. So it still has both the slow and the fast, but both of them are monocalcium phosphate. So having both a slow and a fast-acting acid is very important for a couple of reasons. So the fast-acting acid, most of that carbon dioxide is going to be released within the first minute that you mix those 2 ingredients together. So if you think about making a cake or a bread or something that's chemically leavened, how quickly do we typically get that product into the oven once it's mixed? It might take longer than a minute. So what's the point of having that fast acid? All you're doing is stirring all that carbon dioxide away, so it's not actually doing anything in the product, is it? Because the leavening is going to occur once you have it in the pan in the oven. So that's the slow acid doing its job. So this is a little bit of a nuance, I guess, but the fast acid is really nice because it is going to saturate the water with carbon dioxide. So lots of carbon dioxide dissolved in the water. And so when that water heats up, that carbon dioxide is going to come out of solution and form a little bubble that can then be enlarged with water vapor when the water vaporizes. And the water vapor, actually, when the water evaporates, or when the water vaporizes, it will not form its own bubble. It will just come off. So it needs other bubbles to go into and start to grow. And so those carbon dioxide bubbles that come out of solution when the water gets hot, those are going to provide the seeds for the bubbles that are going to grow from water vapor. So it still plays a very important role. And then, of course, these are going to provide additional leavening at the hotter temperatures. Here's some cake mixes. And these cake mixes are definitely going to have a combination of slow acid, sodium aluminum sulfate, and then a fast acid, monocalcium phosphate. The fast acid in baking powders is almost always, if not always, monocalcium phosphate. So here we have, again, a fast and then a slow here. And these, this sodium acid pyrophosphate actually has a unique functionality in chocolate products. It kind of enhances the flavor a little bit. So sometimes the salt of the acid actually has particular functional properties as well. These cake mixes are designed to be really easy to use, and for people that don't really have any baking experience to be able to make well. And so they're going to have a majority of the slow acid. In these, typically they're going to have like 80% would be the slow acid, and only maybe 80 to 90%, and only 10 to 20 would be the fast acid. Assuming that somebody would take really long time to get that all set up and in the oven and stuff like that. So all these acids that we use in these products, they're all going to be inorganic acids and have these kinds of formulas that, to me, I don't look at that and think, oh yeah, that's definitely an acid. It's not like phosphoric acid or citric acid where I can say, oh yeah, there's the acidic protons. So some pretty complicated equations. SAS, for instance, sodium aluminum sulfate, that one's not an acid at all. And so what happens when you heat it, so this requires heat, then it will be converted to sulfuric acid, which will then react with the baking soda. So a lot of these kind of difficult to see how they're acids just looking at them. So we have this thing called neutralizing value. And what that is, it's a number that when you take how much baking soda you have and divide by the neutralizing value, it will tell you how much acid you need to add to your product. So, if I had a neutralizing value of 100, and I wanted to, neutralize 2 grams of baking soda, I would take 2 and I would divide that by 100 and multiply by 100. So I would need 2 grams of leavening acid to neutralize that. So a few acids, the SAS, for instance, the sodium aluminum sulfate here, the neutralizing value is 100. So, it's very easy to do the math. But something like monocalcium phosphate with a neutralizing value of 80. So that would mean that we would take 2 and divide by 80 and multiply by 100. So we would need a little bit more than 2 grams of monocalcium phosphate to neutralize all that base. And we want to neutralize the base because we don't want to end up with an alkaline product. We don't want to change the pH of that product at all. We just want to leaven it. So we want to add just enough acid to neutralize all the baking soda without ultimately changing the pH of the product at all. Here's some neutralizing values of some different acids. So these are all very common acids to be adding to baking powder formulations or baked goods. And you see their neutralizing values here. And I also have the reaction rate. So we have slow acids and we have fast acids. And some here that say none because there's no reaction at room temperature. So that would be extremely slow. I have variable here because anhydrous monocalcium phosphate, it depends on the coating that they put on the outside of that salt. So it can vary a lot. You would get that neutralizing value from the supplier that you're using for this product. Okay, we have a few products that are actually alkaline. So, baking soda is added to foods. It is a base, and it's added to a lot of foods, but it's added together, typically added together with an acid, so it's not going to make that food alkaline. But we do have some foods that are actually alkaline. So here are some bases that would be added to foods. So again, here's the bicarbonates, sometimes added without neutralizing the product, or without neutralizing the carbonate that's produced. So for instance, in these crackers. So there's an abundance of sodium bicarbonate added, so this product actually ends up slightly alkaline. And then sometimes we're adding actually these strong acid or strong alkali, strong bases, and then we have phosphate salts that are also basic. So like disodium phosphate, for instance, would be alkaline. So here's some examples. Up here, this is cocoa powder. So you've probably heard of Dutch processed cocoa powder. So Dutch processed cocoa powder is treated with alkali. for lots of reasons. During fermentation of cocoa beans, the pH drops. So cocoa powder itself is going to be slightly acidic. And that's this one right here, the lighter colored one. If we treat it with alkali, bring the pH up, actually a little alkaline, it improves the color a lot. So it makes it much more of a deep brown color that's a desirable color. And it also improves the solubility of that cocoa powder extremely. So it's much more soluble, and we're able to disperse it in, a batter or something much more easily. And also it improves the flavor. So having cocoa be slightly alkaline makes the product, have much more of an outstanding cocoa flavor. So if you're using this non-alkalized cocoa powder, typically, like to make a cake or something, you would add an overabundance of bicarbonate to make that product actually slightly alkaline so that the flavor of that cocoa is better. So you can use both, but if you're using the non-alkalized or the non-Dutch processed regular cocoa powder, then you would put in too much baking soda so that that product would be slightly alkaline, so the flavor would be better and the color would be better.
How would you know how much of the sodium bicarb to put in to get it to be a similar alkalinity as the Dutch process?
So the question is, how would you know how much extra sodium bicarbonate to add? So a lot of that would just be experience, but you would know that you need to add a little bit extra. And it's not going to be a ton extra. So, I guess my experience would be about 20% more than you would need, but, it would vary a lot. Here we have some baby carrots. So really common to use sodium hydroxide to peel baby carrots. So when we mix those with a caustic solution, then the skin or the outside of the carrots becomes like mush. And then we can just send the carrots through some abrasive rollers, and that comes off and they're peeled. Here we have a corn tortilla. So corn tortilla is made from treating corn with calcium hydroxide. And that process is called nixtamalization. And it's a, process that's used, for hundreds of years to process corn into corn masa to make these tortillas. And it imparts characteristic flavors. And it also, importantly, frees that niacin, if you remember from our niacin lecture, so that it can be absorbed, so that people do not become niacin deficient that are eating a lot of these corn tortillas as part of their diet. Alkali is commonly used to improve the flavor of olives and also impart this color here, black color. And then pretzels. So these hard pretzels here that you would just get in a bag that are crunchy, they would be, they go under a sodium hydroxide spray before they go in the oven. So the sodium hydroxide would be just there on the outside of the pretzel. And that's what gives it this color. And also that's what gives it the flavor of a pretzel, the alkaline flavor. So the inside would still be white, as you know, because that would not be exposed to that sodium hydroxide. But the outside would brown very quickly because of many things that we probably don't need to go through right now.
So I have one more question.
Yep.
So I made pretzels at home, and when you make the big soft pretzels, you can just put baking soda in the water and
Yep. Mhm.
what is the difference between using sodium hydroxide versus?
Yeah, so soft pretzels are typically boiled in a solution of sodium bicarbonate. And so that's how soft pretzels are going to get their characteristic flavor and color on the outside. You could do that with hard pretzels as well. It is common with hard pretzels to use sodium hydroxide instead of sodium bicarbonate. But soft pretzels, it's typically sodium bicarbonate instead of sodium hydroxide. So, okay. We got 4 minutes. Antioxidants, we have several different kinds. We have some here that are synthetic antioxidants. You've no doubt heard of these: BHA, BHT, TBHQ. These are very efficient antioxidants, extremely powerful antioxidants. All synthetic here. We have some natural antioxidants, the tocopherols that we know of, and vitamin C, and also its D isomer. And then we have some here that are salts that we would not typically think of as antioxidants, but they do in certain products have antioxidant properties, and so I list them here. And then we have products that are not really antioxidants, but they prevent oxidation by chelating metals. So phosphates, certainly EDTA, and then citric acid with all of its carboxylic acid groups as well, chelating metals. These are pictures of the synthetic antioxidants. You see they're all quite similar, but there are phenolic antioxidants. Here's our phenolic group on all 3 of them. And then down here, this would be their antioxidant activity. It's exactly the same as vitamin E. So they work through the same mechanism. We lose a proton and an electron to form this stable radical. And then if we need to give up another electron, we can do that. So that same reaction that we saw with vitamin E happens with these. When we're selecting an antioxidant, there are a few things to consider. Number one, what type of oxidation is occurring? So if we have free radical oxidation versus metal catalysis, then we can choose from this list here. But more importantly, what I want to highlight on this slide would be the emulsion system. Most foods are going to be oil and water. So oil and water means that we have a continuous phase of water, and we have oil droplets that are dispersed in that continuous phase of water. And most foods are that, and most foods would be emulsions even if you don't typically think about them as emulsions. But this would be the most common one. And so for selecting an antioxidant, we would generally want this is backwards. I'm sorry about that. We generally want an emulsifier that matches the continuous phase of the product. So if it's oil dispersed in water, we want an antioxidant that is soluble in water. And water and oil, if we have oil that's the continuous phase, we want to match that antioxidant to the continuous phase. So reason is that typically the oxidation is going to be occurring at the interface between the oil and water, and then also at the interface between the product and the air, where all the oxygen is. And so you want to have that antioxidant dispersed in that continuous phase so it's covering the whole outside of that product. And then it's also going to be there at the interface between the oil and water. So change that in your slides. It's backwards. It needs to match the continuous phase, which would be the one that's second in this name. So Okay, I think we're definitely out of time, so we will continue to talk about antioxidants next time.